Hi, welcome back. This is the last part on rules of probability, applying with multiplication rules. We would now be using the conditional probability ideas of dependency and independency in understanding multiplication rules. Multiplication rule is basically an extension of the AND. So we need to understand two types of events in this case called as independent events and dependent events. An event A is independent of another event B if the conditional probability of A given B is same as the marginal probability P of A, indicating there is no relationship between A and B. So we need to apply a small test. If the probability of A given B has already happened is the same as A happening, then the event A is independent of event B. Another way, if the intersection of P of A and B equal to P of A times P of B, then the event A is independent of event B. This is how the basic formula of multiplication of independent events is derived. Since P of A given B is the common points between A and B over the amount of B, which is P of A times B by P of B and P of B cancel, so we have P of A. Dependent events when P of A is not same as P of A given B, which means there is an influence of the probability of B on probability of A happening given B has already happened. So for dependent events, we need to know whether the event B has happened or will it affect the probability of another event A if it would happen. Of course, when there is statistical dependence, it does not mean there is causality. For example, you could know a person's age and would be able to estimate the probability that the person's individuals use texting or text messages. But this does not prove that age and texting are related. The multiplication rule for independent events, if you have n independent events happening at the same time, then P of A1 to n equal to P of A times P of A2 times P of A3 times P of AN. And this is only when the events are independent, also called as the special rule for multiplication. Just to understand this, suppose there's a website which has two independent file servers, and the servers have 99% of reliability for each of them. Now, what's the chance that the system would totally fail? Now, this means server 1 needs to fail and server 2 also need to fail. There is no dependency between the failure of server 1 and the failure of server 2. So then, such events are independent. So F1 be the event that the server 1 fails, and let F2 be the event server 2 fails. So when you apply the rule of independence, it's F1 and F2. That's P of F1 times P of F2. The failure is given by 1 minus reliability. So my reliability was 99%, failure is 1%. 1% times 1% gives you the failure of both. Now we would like to know how much the system is reliable. So the total reliability could be 1 less than 0.0001, about 99.9% reliable. This is also called as the special rule of multiplication because it requires that events A and B are independent. In the sense, the probability of A does not affect the probability of B, or the happening of A is not influenced by happening of B. The rule is written as P of A and B equal P of A times P of B. A survey of the American Automobile Association, and they revealed that about 60% of its members made a reservation in their airlines. If you randomly select two people and assume them to be two different events, R1 and R2, what's the probability that both made the same airline reservation? Now, the reservation done by person 1 does not depend on the reservation done by person 2. And in this case, the probability of making a reservation is given to be 60% for anybody. And hence, P of R1 and R2 is probability of R1 times probability of R2, which is zero point 0.6 times zero point 0.6. That becomes 0.36. Always please remember, when you use the multiplication rule for independent events, the resultant probability would be less than the least of the individual probabilities. The general rule of multiplication states that P of A and B equal to P of A times P of B given A, and this is derived from the conditional probability. When two events are not independent, which states that two events are dependent, then there is a giant probability of both happening at the same time, and hence we would use the conditional probability to derive at the probability of both A and B happening at the same time. P of A times P of B given A. Now let's say a golfer has about 12 shirts in his closet, and 9 of them are white and the others blue, indicating 3 blue, as given in the diagram. Now he just grabs 2 shirts on 2 days in a row. Now what is the likelihood that both the shirts selected are white? This particular event of selecting the first shirt, let's say, which should be white, is W1. Probability of PW1 is given by 9 white shirts of the total 12. The second event of selecting another white, W2, would depend on what shirt was selected for, because once a selected shirt is taken out, it is not replaced back. When you do not replace, it becomes conditional. It depends on what you took the first, will determine the probability of what you take the second. Since in this case one shirt has been taken off, the total number of shirts remaining are 11. And the first shirt was also white, so there are only 8 white shirts now of total 11 shirts available. So the probability of taking a second white, given the first was also white, is given by 8 of 11. And P of A and B, that's the probability of 2 white shirts, would follow the formula P of A and B equal P of A times P of B given A. That is 9 of 12 times 8 of 11, about 55% chance. This is the similar idea that's normally used even with decision trees, which you would be probably looking at in the next module. Thank you for watching.